Hello to everyone. In this short video, I'd like to introduce a quantum mechanical theory which is based on the postulates and mathematical representation of quantum mechanics. This theory does not add or take away from it, but rather tries to expand a little on its approach. We'll start with simple basics, very simple patterns, which later on will be generalized, and you can see that although at first may seem a little strange, later on will lead to far more interesting conclusions. Let's start with a light, which can be interpreted as an electromagnetic wave and may be created and absorbed in several ways. I'm going to show you a simple schematic, a light emission by an excited state atom. You may notice immediately that something is missing from the sketch. You may miss many things. For example, I've not decorated it with little flowers, but the most important part which is not shown is what will happen to the light. Light is able to cross galaxies in the same state, and because the state does not change, we cannot talk passage of time from the light's point of view. Actually, we can say that time does not pass for light. But sooner or later the light will be destroyed. At some point it will be absorbed. Now consider a simple example and expand the figure. The photon energy travels from atom A to atom B. We can also conclude that the same process takes place in reverse from atom B to atom A. The same physical process describes the phenomenon. If there were only these two atoms, they would play soccer with the photon. If you have a lot of atoms, depending on the configuration and accordance with the conditions of the energy, the photon will be transferred randomly side to side between the atoms. It still must continue to meet strict criteria. The photon that starts from the A must transfer its energy only to selected B atoms that satisfy those strict conditions. If it was not an appropriate atom, the photon would just keep moving on. How far? No matter how far, as long as it finds a suitable pair for the process. It can also be said, and this is the first postulate, that there is essentially always a found pair for the photon emitter atom. Thus, the case is not possible that the excited atom just emits a photon, because eventually, as the time is not taken for the photon, there will always be a pair for the absorption. The postulate finally is that the absorption is not simply the consequence of the emission, but the unavoidable requirement of it. There is no way to emit a photon without there being an appropriate pair ready to receive the energy packet. Let's look at a simple case where we can apply our new postulate. Let's examine a double-slit experiment. The light as a wave phenomenon passing through the slits, interference created, and on the maximum and minimum points, this becomes visible as stripes or fringes. Position of the maximum and minimum places are dependent on an integer multiple of a constant. When this is marked on a new figure, you can see that the maximum points are on privileged positions compared to the minimum areas. The reason is that the maximum points are located at a distance that is an integer multiple of a constant through each of those slits. Actually, if the excited atom A tries to find a pair through the gateways, the atoms at the maximum positions are twice as likely to fulfill their role to be selected as a couple. Since a postulate says that the pair findings is not simply a consequence but a condition of the photon emission, and the phenomenon of the light is a reversible type process, it must be explainable, and it can be explained in reverse. If we consider it backwards, like radiating light from point B to point A through the gateways, and since point A from point B is only in strict conditions, in a special state it is possible to reach for the photon. It can be seen that the maximum places have a double chance, because through both of the gateways it can arrive at point A in the same state. With the help of our postulate, we found an explanation of a formation from interference fringes, which illustrates the phenomenon, even if we send the photons one by one. Moreover, we will not need to consider it as interference, since the pair finding schematic itself gives an explanation of the formation of the maximum and minimum places. Now let's look at another example. Of course, we can imagine more complex structures in place of the atoms as shown. This is just a simplified scheme. The atom B can be replaced by a molecule, metal, or crystal lattice. The point is that the quantum state has to be unified and can only be changed by the incoming photon and can be transmitted in a way that fits to the figure. We are saying we can imagine an experiment in which clever physicists preparing a state in which two photons simultaneously reach a structure such that their efforts join and produce a third photon. Obviously, the combined energy of two photons leads to a double energy photon, which then excites the atom C. This is a very special case, but it is possible that clever experimental physics in a research lab can produce such a thing. We will return to this figure later. Let us look at another figure in which a photon split can be seen. By the split, the photons stay entangled and described by one mutual quantum state. This phenomenon is usually produced by using a special nonlinear crystal. A laser light hits the crystal, a single photon splits in two, dividing the original photon's energy between them, and in a strictly defined angle and complement state, they leave the crystal. The figure intentionally omits what will happen with the two photons after this. Therefore, in this form, the experiment cannot be done. To determine that the two photons are entangled, we have to measure them one by one, or at once, that is, when both of the photons are annihilated. Now let us return to the figure seen before. Actually, we can see the same experiment, but reversed. C is the atom inside the laser machine that releases the photon. B is the part of the nonlinear crystal which splits it and forwards them in two different directions, and these photons will excite the atoms in the detectors, making it possible to determine their entangled state. Please note that the entanglement can be detected only when the photons have already arrived and have not been annihilated. According to our postulate, this is also a pair-finding process. This situation is more complex because in this case, not only one, but two appropriate atoms have to be found to accomplish this process. Both the A1 and A2 atoms have to be ready to receive the special state photons, and in such a state that together they will satisfy the condition that was described in the place B by the photon that came from C. Because of the pair finding each other, the process has to be interpretable in reverse. Only a special packet with strict defined parameters can arrive from the A1 and A2. You might think that if we place a filter between the A1 and B, it will have no influence on the other arm, B to A2. But the result will be that only that kind of A2 may be chosen that fulfill the new situation. This way it is recognized that precisely the new tool used for the observation has changed the experimental conditions which we experienced. The pair-finding rule explains the entanglement. The pair-finding postulate explains expressively the phenomenon of the quantum eraser experiments too. These kind of experiments are usually set up to investigate and demonstrate that because of the uncertainty principle, simply the possibility of getting some information influences the result of a physical process. Furthermore, an experiment like this will be examined with our new approach. In a simplified form, we can say that the experiment is a kind of combined implementation of the double-slit experiment and the quantum entanglement. In a quantum entanglement, as we discussed earlier, the entangled pairs are in strict connection with their exciting photon. The photon emitter atom in the laser device can find a pair to hand over its energy packet in a special way, but only if both of the photons after the split find an appropriate atom in paths closing at a given angle. The member of the pair that goes upwards towards D0, as in this figure, finds a pair for itself in the detector D0, the downward heading photon pairing from one of the D1, D4. The arriving angle and position of the photon that reaches the detector D0 is dependent on the arriving angle of its entangled pair that hits one of the D1, D4 detectors. So if one of the lower placed D1, D4 detectors produce some kind of a shape, as in interference fringes or probability distribution, then the result on the D0 detector will be similar. As we discussed at the double-slit experiment, the phenomenon can be examined in reverse, just like if the photons would start from detectors to the laser machine. We can see that those photons which are coming from the D1 or D2 detectors and paired with the atom of the laser are most likely from atoms in privileged positions. These positions are at such a distance that is an integer multiplication of a constant from both of the gateways. By this, they are an interference-like maximum points. At these points, the photons can prevail only if inside the crystal at the split event, their couple is created to arrive at the proper angle. The photon then produces an interference-like pattern on the D0 detector. By continuing this line of thought, there is no chance to reach both of the gateways from the D3, D4 detectors. Therefore, there are no maximum places. Also, their entangled pairs at the D0 do not form a striped pattern. It can be seen that by interpreting the experiment as a mating process, there is no need of counting with any other effect. We do not have to explain the phenomenon, as it is dependent on the knowledge of the witch slit information, and also it is unnecessary to assume that the photon acts sometimes as a wave phenomenon, and by that it makes interference. However, the delayed choice quantum eraser experiment reveals other strange things as well. If we place the lower and upper items in such a way that the photon arrives at the D0 detector earlier than at the lower mirrors, the result of the experiment will be exactly the same. That is, before one of the D1, D4 is selected for the photon as a target, its entangled pair hits the D0. Therefore, it has to have this information earlier to behave properly and to participate in the creation of an interference pattern or a random distribution. This is a time difference problem, but with our postulate, we are describing phenomena from the point of view of the photon, so we cannot examine passage of time. The delay can also be enhanced up to the extremity. Think of a gravity lens and a star behind it as a cosmic two-slit experiment. We can find a situation in which a photon emitter atom has to find just such a pair that at the time of the emission may not exist. Obviously, despite the fact that the state of the photon is not changing during its travel, we can say that it gets its pair prepared by the environment. We have to show a model of how to build up the pair finding while the photon moves through the intermediate portion of the space. To outline the process of mate choice, two phenomena must be connected together. The first is that an independent structure has only certain information from distinct, faraway elements that represent their past state. If we look out at the stars, then we are examining states from millions of years ago. The same happens with the particles too, unless they form a direct connection system, that they are in a common state. Then what they interact with is the past condition, the old state of their partner. This kind of state information, like anything else, can extend with a maximum of the speed of light between two structures. The other phenomenon is the separate identity of the impacts. The nature is not calculating average, not neglect, and especially not solving differential equations. These operations are necessarily only to make available for us to build up an interpretable model. But in fact, every single particle in every single moment exerts its effect independently in the universe. So what actually happens when an excited atom is waiting to find a pair to hand over its excess energy to another atom? It researches the past state of the universe just as we do when scanning the stars in the sky. The release of the photon can happen when it gets some information about a suitable pair. Actually, it is not getting information about how far away the pair is. It has moved away from that time, how long the information traveled in space, or does the couple still exist at all? The same process takes place whether the two atoms are adjacent to each other, or when one is light years away and its old image has just reached the other. However, there is still a significant difference. The probability of finding each other is different between close and distant pairs. The mating condition imposing postulate, therefore, will be supplemented to assume a cause event from the chosen pair, a trigger, which is composed of these factors. It is independent from the traveled distance, emitted continuously, defining a state, a discrete information package describing the element that is appropriate to receive the photon, spreads uniformly in every direction in space, and by this it arrives at the particle that is waiting to release the photon. The photon, which is freed by the effect of the arrived trigger, is moving step by step on the fronts of the trigger, receives the most current information about its mate, and finally reaching it. So the supplemented pair finding principle that we now call the pair trigger principle is now suitable for modeling the time difference problems. The pair trigger principle obviously raises a lot of questions. These will be dealt with later. Thank you for your attention.